Hey everyone, hope you're doing well. This video is going to be me going through all the examples to help you do exercise 3A. So 3A is talking about introduction to functions, so we're looking at function notation. We're looking at how to determine if a graph or a relation is a function, and we're looking at introduction to inverse functions. So this is me strictly going through the examples. You may need to refer to your textbook for rules and definitions that I'm going to be referring to. All right, so let's start with example 3.1. If f of x equals 2x plus 7, find f of 3. Okay, this one's relatively straightforward, this type of question. So anytime you see x, you're going to substitute it with 3. So f of 3 is 2 times 3 plus 7, which is 6 plus 7, which is 13. Example 3.2. If you're just looking for a specific example, then just find it in the video. Otherwise, this video would probably be quite long. 3a. Determine with reasons if either of the following graphs shows a function in the form of y equals f of x. So we're trying to decide whether both of these are functions or not. So what I like to do is use the vertical line test straight away. So let's us just draw, excuse my vertical lines, but just draw some vertical lines on each function. All right. So what we're looking for is every vertical line that we draw only passes through one point on the graph. We can see that it works for A, but it doesn't work for B. So that means A is a function and B is not a function. Now, once you've established, let's just go back to A. Let's stick on A. When you've established that a graph is a function, you can also say whether it's a one-to-one or many-to-one function. So a one-to-one just means that for any particular x value on that function, there's only one y value. Many-to-one means you can have multiple x values that give you the same y value. So let's have a look at this one. So just have a think about this one, just by looking at it, right? So we have many-to-one because I can see that these 4 points all have the same y value, all right, but they all have different x values. So this one is a many because there's many x's to one y value. All right, this is a many-to-one, it's a function. Anything that's not one-to-one or many-to-one is not a function. All right, following that. So let's see this one. Let's have a look at B of our circle. So let's just say I pick a point here on the x-axis here. Let's call it x1. See how at this x value there's two y values? All right, so we just call this a one to many. All right, and it doesn't pass the vertical line test, right? A one-to-many function will not pass the vertical line test, obviously, because you draw it up. All right, every time you draw a vertical line, it's going to pass through more than 1 point. So this is why B is not a function. Okay, work to example 3.3. Find the largest possible domain of f of x equals square root 2 take x. Right. So we're trying to find out the largest possible domain, which means we're trying to find out the set of all possible x values that we can input into this function in order to get an output. So for all the values of x that work. So for each function, it might be different. In this function, we have square root of 2 minus x. Now that square root gives a lot away. We know that we won't be able to square root a negative number to get a real solution, and we only care about real numbers right now. So I know that I can't square root a negative number, so that means whatever 2 minus x is has to be greater than or equal to 0. Okay, because we can square root 0, and then we just solve this inequality. So negative x take away 2 from both sides. All right, and then divide or multiply both sides by -1. When we multiply or divide by -1, flip the sign. You can do this however way you want, but this is the domain, largest possible domain for x. All right, x can be anything that is equal to or less than 2. So that means it can be negative. All right, so if we test that, let's say we do -5. All right, 2 minus -5 is 7. Okay, we can square root that. Okay, I'll just quickly give you a visual as well. So if I pull up my graph, if I graph this function, okay, you'll see that the graph does not exist when x is bigger than 2. All right, so that's confirmed our result. Example 3.4. Find the range of f of x equals 2 take x. So same function as before, but this time it's restricted our domain. It said that we are only interested in the part of the graph when x is negative, and including 0, obviously, because of x is less than or equal to 0. So let's pull up our graph again. All right, so if you're ever given a domain restriction like that, well, you don't want to use the whole graph. So this is where we go into our window settings. All right, so our maximum value for x we're going to set as 0 because we don't want anything that's past 0. We want anything that's 0 and below. Now x min, I don't care what number I put here because we know that it can just go forever, right? So let's just say -20. All right, you can put any number here that you want. Okay, so, and you see that this graph goes on and on forever in the negative x direction. So the range is the set of all possible outputs for this particular graph within this particular domain. So we can see that visually, if I were to use my calculator to help me find it, let's go into graph trace. When x equals 0, right there, okay, our y value is 1.41. That's actually the square root of 2. Okay, and we'll get that algebraically. So that means the range of this graph within this domain is square root of 2 or anything larger. Because if you'll see that this graph goes up forever and ever to infinity, because say I do negative 100 now, all right, see how it just keeps going up and up and up? So we can do this by either looking at the graph, or let's just calculate, let's just show how we got the root 2. So when x equals 0, we have square root of 2, our function, and then I'm going to copy this graph in, whoops, to give you a visual aid. Okay, so range is f of x, or you can write y as well, but it's greater than or equal to square root of 2. Okay, so use a graph to help you, and you'll be able to find the range. Okay, work example 3.5. The population of pigeons, P of t, so pigeons population of pigeons with respect to time. So what that means is that our y-axis is going to represent population, and our x-axis is going to be time in years. So the population of pigeons, P of t, on an island at a time t years after being introduced is modeled by P of t equals 100t squared. State 4 reasons why this model is unlikely to be perfectly accurate. Okay, so the first thing you should do here is sketch the function or draw it. Use a calculator if that's allowed, or if not, this is straightforward enough to sketch manually, so I'll just do that. So 100t squared, this is just a basic parabola. So I have my t, and my y-axis is population at any point in time, so P of t. Now, the turning point is going to be here at 0, 0. All right, and now I'm just going to sub in some values. So if I sub in 1 for t, I have 100. If I sub in 2 for t, I have 100 times 4, which is 400. And then, so that means I have that point, and I'm going to run out of room, but you get what I mean. So if I sub in 3, it's 100 times 9. I should have 900, so my graph's going to go all the way up. And since it's a parabola, it's going to be symmetrical, so let's just put 100 there, 400 there. All right, and then we're just going to keep going up further. Excuse my sketch. Still haven't quite mastered sketching this on a screen, so there's my perfect parabola right there. Okay, or just get this using a graphics calculator. Okay, so let's state 4 reasons why this model is unlikely to be perfectly accurate. Well, you can come up with many things here as long as it's, I guess, mathematically reasonable. So one thing you'll realize is that the graph, if we go in the positive t direction, the graph goes up and up and up forever, right? So that's suggesting that the growth of pigeons, well, it's going to be infinite. So pigeons, I'm going to say growth of pigeons is not unlimited. So that's one reason that this model is unlikely to be accurate. So another reason is, well, population growth. It kind of happens in cycles, so or like different seasons when it comes to animals. So it doesn't take into account seasonal changes. All right, so you can see that, okay, say we start at 0 and we just keep increasing in time. You see that the rate just keeps going higher and higher and higher. So it's just saying, all right, it's just going to keep growing at an increasing rate, which is not realistic. And then we can say, well, this graph, if we leave it as is, goes into the negative t values. So we know that that's nonsensical here. So we can say that the domain should be restricted, or otherwise we're going back in time. restricted, so t can't be negative. And one other point that's maybe not so obvious, but when you think about it, oh, it's actually right in front of you, is the fact that we're starting with no pigeons at t equals 0. So t equals 0 is always our starting point or initial point. And if we sub in 0 for t, we're going to get 0 for p of t. So it's saying that we're starting with 0 pigeons. So that doesn't make sense, because if you're starting with 0 pigeons, how can you all of a sudden have pigeons? Right? Magic. Boom. Okay, so 4 reasons there why this model may not be perfectly accurate. You can come up with many more as well, I'm sure. 3.6. If f of x equals 3x plus 5, find f to the negative 1 of 11. Okay, so what this is saying is it wants you to backtrack, essentially. I'll show you 2 ways. You choose whichever way works for you. Okay, so the output is 11. All right, so it's asking you essentially if the output, or if the y value was 11, what was the x value? So let's sub in 11 into our function output, or f of x. So 11 equals 3x plus 5, and then solve that for x. Take away 5 from both sides to get 6, and then divide by 3. X equals 2. So f to the negative 1 of 11 is 2. Okay, so that's method 1. All right, method 2. I think we actually do this a bit later as well. So instead of writing f of x, I'm going to write y. And then I'm going to do y equals 3x plus 5. And then if I want to find the inverse function, because f to the negative 1 means the inverse function, I swap x and y. And then I solve for y. So y equals x take 5 on 3. All right, so now this is the inverse, equals x take 5 on 3. All right, you probably prefer the first method already. So the inverse, when it's 11, then we have 11 take 5 on 3, which is 6 on 3, which is how we get 2. So the second method does have its purposes, but later we'll find it useful when we're actually just trying to find the inverse function. So for now, probably just stick to method 1. And finally, example 3.7, sketch the inverse function of the following graph. Okay, inverse functions, I'll show you 2 ways. This is going to be tricky because I'm trying to do it on a screen, so let's see how we go. Let me put up some grids. Nah. Picture. Okay, no, that's not going to work because this is a picture. Or I'm just terrible at this program. So, look, what we can do is draw. What's happening here? Draw. Let me get my ruler. Alright, I want 45 degrees because that's y equals x. It's pretty cool that you can do this here. And then basically I'm going to draw y equals x there. Alright, so basically I'm just trying to reflect the blue graph across this line, y equals x. So if I were to do that, then let's do it in red or something. Get rid of my ruler. So remember when you reflect a point across a line, every single point needs to be perpendicular to the line. So that means I need to flip it. That means this point here is going to go, so perpendicular means if I draw like dotted lines or something, it's going to be here. And then the same thing around about here. And then by the shape of this, it's going to go something like this and that. Alright, so there's my inverse. It's not perfect, but well, I won't mess with it anymore, but hopefully you understand the idea. And well, I said I was going to show you a second way, so I guess okay. So when you find inverse, when you're trying to sketch it, the x and y values will switch. So if you see this blue point here, see how it's the coordinates is pi on 2, 1. Well, that means this red one is going to be 1 pi on 2. Okay, so you can kind of use that idea, and same with the other point. You can use this idea if you're stuck drawing it, flipping it across that line. You can use that for a few points to give you an outline of what your inverse should look like. So I hope that helps you with how to sketch inverses. Okay, so that's all the examples before 3A. Yes, there's a lot. This is a very important key topic. It covers a lot of content. All right, so now you can go ahead and do all the questions I've sent you for exercise 3A. Have a good one. I'll see you soon.